Welcome to this presentation entitled Delivering eCook at Ground Level. I am John Mullett and I work for a social enterprise called Sustainable OneWorld Technologies, or SOWTech for short. Our mission is to create income-earning opportunities for sustainable development in hot, low-income communities. Most cooking in sub-Saharan Africa is undertaken on the ground using either a three-stone fire or an improved biomass cook stove, such as those shown in the photographs. The aim of the project was to develop a solar-powered cook stove system that was both affordable and acceptable to low-income families. Our strategy to achieve this was to design the components of the system so that as much as possible could be built locally. Bringing another imported product from a factory in the Far East is not, in our opinion, the best way to serve the poorest people. Let me break with tradition and put our acknowledgements up front. Firstly, we would like to thank MECS for giving us the resources required to undertake the project. Secondly, we would like to express our thanks and appreciation all the help that our partners Acquaid Lifeline provided to the project. The folks at Acquaid's Namissu's Children's Village were generous with their time and support during our initial user-centered design study and then subsequently in the field trials. They helped us with information such as what time of day they cooked, what they cooked, how many people they cooked for, and how big were the pans that they used for these meals. However, the strongest message we received was the importance of integrating a phone charger. The suggestion was that the men would be influenced by such a feature as well as the women, thus helping to achieve social acceptability to this change of cooking. So, if we want to choose when to cook, we must find a way to store solar power. There were a number of storage options considered. We decided that batteries to store electricity were too costly and too difficult to maintain. They had a limited life, and the environmental issues associated with the end-of-life recycling were problematic. We decided that heat-retaining metal structures, such as the Arga stove, would be too difficult to build and insulate and transport. We decided that concrete or clay-type structures would not be able to hold enough heat to deliver the heat for cooking. We did choose to use phase change materials, or PCMs, to store the solar heat until it was needed for cooking. The phase change material we chose was erythritol. It has been successfully used in earlier work by Professor Schwarz and his team at Cal Poly. It releases heat at 118 degrees C. It is mass-produced as a sugar alternative. It is readily available, and it is a food additive, so safe to use in the proximity of cooking. And it is a fermented product which has the potential to be produced locally. In the graph on the slide, you may be able to see a blue line which shows the temperature of the PCM. During heating, it rises. Once the heating stops, it falls and then flatlines at just under 118 degrees C. This lasts as long as it takes for the PCM to solidify. The heating and cooling cycles can be repeated multiple times without degradation. To achieve our affordability targets, we needed to change how we use the PV power. We developed a device to replace the regulators and batteries required by most PV-powered systems. This means that the solar power is used directly from the PV panels, rather than indirectly through batteries. There were three parts to this work: the thermodynamic calculations, the development of the power optimization device itself, and the research concerning the availability of PV panels and their specifications in Malawi. The graph illustrates the stable draw of voltage from the panel whilst delivering variable voltage to the heater, and the pod can charge a phone. In order to cook, the electricity from the PV panels needs to be converted into heat. We built and tested a wide range of heaters based on using materials available in Malawi. A resistive wire heater and a temperature sensor are encapsulated either between two ceramic tiles or embedded in clay and then fired. The picture on the right shows an infrared test of a clay heater. These heaters were inexpensive and could be made locally. We designed and built a cooker in Malawi which housed both the heater and the phase change material for heat storage. As the photo shows, the heater was wrapped in a blanket to enhance the heat retention of the oven. Sitting next to it is Lupaccio, a student from the village who spoke English. Later, he spent time explaining to Raja, the guard, how the system worked. We were pleased to have achieved some cross-language understanding of what we were doing, as we considered local engagement to be a very important part of what we were doing. After all this work, we did also do some cooking, using our platform of direct-use solar. We did cook nsima, a maize flour dish. We also did some work with a hot plate, as the video shows. So, are we continuing things after the MECS project has finished? The answer is yes. We have secured other funding to allow us to design and build and test a Mark II pod. With a number of African partners, we are currently working on the following: preparing the training program to start manufacture of the pod in conjunction with partners in Africa. We are developing performance insulation products to use both with the cookers and cooling applications from materials found in Africa. We are seeking support for building a modular agro-processing hub using direct-use solar for crop drying in partnership with a consortia of 20,000 smallholder farmers. We're using direct-use solar for heating technology to improve the performance of anaerobic digestion, which is treating fecal sludges. And we are using the solar platform to create proactive evaporative cooling for agri-product storage. On behalf of the SOWTech team and our partners, thank you for watching. We would welcome any questions or further contact.